So we have a complex problem here. And my biggest tip for complex problems is to figure out what your variables are, right? What is x, what is y? The biggest clues for these are to write inequalities that you know you're going to end up using. Inequalities that are super clear, right? We know that the rabbits should be fed no more than 5 ounces of food a day, right? We also know that food costs $20 per ounce and $30 per ounce. What is common in both of those? Ounces. We know ounces are going to be x and y. So go ahead and write x plus y has to be greater than or equal to 5 for that. Go ahead and write 20x plus 30y is going to get you your objective function. Okay? And then the other equations you can kind of figure out from there, right? If food x is 8 grams of fat per ounce, then 8 times the ounces of x will tell us the fat. 12 times the ounces of y will tell us the fat in that one. And we have an inequality for grams of fat. Even though it spits out grams, that's okay because our variables are still ounces. Don't get confused. As long as your ounces are all the same, it's okay. Your output can be different. Right down here we have money. Here we have protein, carbs, all in grams. And this is in ounces. As long as our variables stay the same, we're okay. So, now that we've written the inequalities, the hard part's over. We just have to plug it into Desmos. We get this graph here. And you have to kind of play around with it and look carefully when you have more than a couple inequalities. You got to really look carefully. And this would be your feasible region. Okay? So we're going to take these vertices and plug them into our objective function here, which looks like this. And now remember, the problem asked for the best combination of food, and we know from context they want to spend the least amount of money possible. So the least amount of money possible is 60 cents to meet all of those criteria. And that is right there. Okay, 3 ounces of food X, no ounces of food Y.